The anomaly over people. Planes, power, and people. While satellites learned the shape of the dent first, the consequences drifted down into dispatch rooms and control centers where routine lives. Airline dispatchers already skim solar indices the way they skim wines aloft. On days when the anomaly deepens and the sun is active, routes kink, altitudes shift, and crews get briefings that read like quiet warnings. Over water, HF radio can fade, messages repeat, position reports lag. The airplane lands, passengers never know. In the ops log, align, static, reroute, dose within limits. The dose piece is measured, not guessed. Aircrew already carry higher cosmic radiation exposure than most people on the ground. Regulations track it, and schedules spread it. The anomaly doesn't turn a flight into a hazard by itself. But when solar protons ride a weaker corridor lower, dispatch adds margin. Eastbound red-eyes slide a few thousand feet, or step south a track, trading fuel for dose discipline. It's not drama, just arithmetic. Navigation feels the dent in subtler ways. When solar storms couple to a patchy field, the ionosphere warps. Scintillation scatters signals, pseudo-range errors grow, and your blue dot jitters. For an airliner on final with augmentation, integrity flags watch the data. If those flags slip, procedures step back to raw data skills pilots still train. Different minima, different cadence, the older muscle memory carrying the load. Survey crews, offshore rigs, and precision farmers already build windows around these hiccups. A wider, deeper anomaly expands those windows across time and latitude. Across town, grid operators watch a different heartbeat. Long transmission lines link distant regions. When the field swings fast, it drives currents into those lines that transformers weren't built to love. Most days, protections chatter and reset. On a hot summer night with tight reserves, that chatter can start a cascade. A weaker, patchier field doesn't create the storm that causes it. It lowers the threshold where nuisance becomes damage, especially in places where entities stretch and budgets stretch further. So utilities add friction to the path. Series capacitors block DC on key lines. Neutral grounding resistors tame saturation. Geomagnetically induced current monitors alert operators to derate before heat and harmonics pile up. And they drill black start, the choreography for turning a cold, dark network back on. So the worst day is also practiced. Pipelines feel the same physics drawn in different ink. Cathodic protection fights corrosion by pushing the right current the right way. Space weather adds noise. Operators adjust set points, automate responses, and accept that a few more days per year will feel fiddly. Railway signaling can glitch under fast DBADT. Systems default to safe. Telecom sites add holdover clocks, so a jittery GNSS day doesn't ripple through timing for an entire region. None of this makes a headline. It makes the lights stay on and the calls go through when the sky is noisy. There's a systemic irony that operators know in their bones. The anomaly is regional, the ripples are not. A flipped bit over the South Atlantic delays a weather model ingest, nudging a forecast that nudges a hub bank, moving megawatts by inches at the wrong hour. A line trips in one grid and tie lines hum harder in another. Complexity amplifies what physics starts, and the fixes travel the same networks. So the playbook grows up. Airlines fold radiation and GNSS integrity into dispatch tools, not as exotic flags, but as tiles next to winds and turbulence. HF gets a SATCOM fallback pre-briefed. Cabin crews see dose advisories without drama. Airports rehearse GNSS-degraded ops until calling for a localizer feels like normal, not nostalgia. Grids write staged policies tied to space weather alerts. Defer maintenance, hold reactive margin, watch specific corridors. Pipelines' control rooms accept that their cathodic protection graphs will wiggle and automate the response. Ports with cranes and pilots facing tricky approaches coordinate windows around the same sky. The public peace is modest and honest. Magnetic weather is not apocalypse. It's another forecast. Watch, warning, actions. The message sounds like hurricane season because the behavior should match. Harden where it matters. Stage resources before the window opens. Accept inefficiency on the days that pay it back. Underneath the procedures sits humility. A hot province at the base of the mantle. Doesn't ask for permission. It steers heat. The core adjusts, the field above sags in 2 rooms, and a dispatcher in Sao Paulo changes a flight level. The connection is long, quiet, and real. We won't fix the engine. We'll learn its moods, measure them, and fold them into the way we fly, wire, and schedule. The dent isn't destiny, it's a constraint. Good operators live on constraints. Inside story, how Earth makes a magnetic field. To understand why satellites get punched over the South Atlantic, you have to stand, at least in your mind, 3,000 kilometers down, where liquid iron moves like a slow river wrapped around a solid inner core. Motion in a conductor makes electric currents. Currents build magnetic field. That field threads the fluid and pushes back on the motion. It's a feedback loop called a dynamo. Keep the flow vigorous, and the loop sustains itself. Choke the flow or reorganize it, and the field above changes shape. Sometimes gently, sometimes enough to leave a dent you can fly through. What powers the churn isn't one engine but a stack. As the inner core grows, iron crystallizes and releases heat and light elements into the outer core. That buoyancy drives convection. Radioactive decay adds background warmth. Rotation twists rising and sinking fluid into columnar rolls, aligned roughly with Earth's spin. Those rolls, jet-like sheets and plumes, carry magnetic flux the way wind carries clouds, bundling it into ropes and sheets, shredding it, reassembling it, always moving. From space, you see a tidy dipole like a bar magnet. From the core's perspective, it's weather. The lid on the pot matters. The lowermost mantle above the core is not uniform. It drains heat unevenly across longitudes. Where the mantle is cooler, heat escapes faster, and convection strengthens below. Where it's hotter, heat leaks more slowly, flow diverts, jets bend. Over Africa sits a continent-scale province of hot, possibly compositionally distinct mantle. That blanket changes how and where the core can shed heat. The core listens and responds. Jets sharpen along some rails, stall along others. Magnetic flux piles up here, thins there. At the top of the core, you can map spots where the radial field points opposite to Earth's main dipole. Those reverse patches are clues to how the flow is steering the field. Link that to what we feel in orbit. When reverse flux gathers under the South Atlantic sector and migrates, surface field lines tilt downward. The field above weakens locally, lowering the altitude where trapped particles skim. That's the South Atlantic Anomaly's shape, written by Deep Flow. The recent split into 2 lobes, western and eastern, tracks with how reverse features at the core mantle boundary slide past each other like weather systems, leaving 2 rooms of weak field at the surface instead of 1. How do we know any of this if we can't go there? We infer with discipline. Satellite missions map the magnetic field in exquisite detail. Ground observatories record the slow drift, secular variation, decade after decade. Models subtract crustal magnetization and ionospheric currents to isolate the core field. Mathematicians invert those measurements to estimate the pattern of field at the top of the core. Seismology, meanwhile, images the mantle's slow structures, where independent lines point to the same geometry: hot mantle under Africa, altered heat flux, reverse core surface patches, and a South Atlantic dent overhead. It stops reading like coincidence and starts reading like causation. The dynamo's sensitivity is the point. It's not a clock, it's a fluid machine with memory. A jet strengthens, advex flux across a boundary, and the surface field over an ocean sags a little more. A plume wanes, new flux emerges elsewhere, and the sag relaxes or moves. None of this requires the global dipole to be failing. Globally, Earth's dipole has eased since the 180s, but the South Atlantic dip is regional and faster. Both can be true because the field is layered. A dominant dipole plus migrating non-dipole patches that pack a local punch. Rotation imposes order, but turbulence adds mischief. Imagine elastic threads, the field lines, stitched through the fluid. Shear stretches them, reconnection snaps and reties them. Bundles drift like storm bands. Where bundles converge in reverse direction, they seed those flux patches that matter at the surface. Where the mantle above acts like a warm lid, flow pathways reroute. The African province's edges, in many simulations, behave like rails guiding jets. It's at edges where contrasts are steepest that flow organizes and flux concentrates. The surface sees the edges as boundaries between rooms of weaker and stronger field, drifting in longitude at humanly inconvenient speeds. There's comfort here. A responsive dynamo is a healthy one. The very changes we dislike in orbit prove the engine is alive and coupled to the planet above it. The risk isn't that the field disappears, it's that our systems run closer to the seams where the field is odd. The deeper lesson is practical. Treat core weather like any other forecastable hazard. Keep measuring. The satellites and observatories are our eyes. Keep modeling. The inversions are our maps. And keep designing with the fluidity in mind, because the core will keep moving heat along the paths the mantle allows, and the field will keep answering in patterns that matter to hardware, pilots, and grid operators. The core mantle conspiracy. Africa's deep blob. Follow the heat to the base of the mantle. Seismic maps reveal two megastructures where quake waves slow. One is under the Pacific. The other sprawls beneath Africa and the South Atlantic. They're called LLSVPs. Huge hot piles perched on the core like heavyweight blankets. Not magma oceans, solid, but hotter or denser than what surrounds them. That uneven lid changes how the core dumps heat. The dynamo below is sensitive to its lid. Cool mantle above? Heat escapes fast and flow strengthens. Hot mantle above? Heat leaks slow and flow bends. Put a hot lumpy province under Africa and you skew the engine. Jets sharpen at its edges. Plumes bend. Magnetic flux gets pumped into different longitudes. At the core's top, we map reverse flux patches. Local spots pointing opposite the main field. In the African sector, they grow and migrate. At the surface, the field sags. That's the South Atlantic Anomaly. Now the world-altering part. Independent lines agree. Seismic tomography draws the African blob. Satellite and ground data inversions show reverse patches marching under southern Africa and the mid-Atlantic. Surface maps show a single bruise splitting into two lobes, east and west, out of sync, with the eastern lobe leaning toward Africa. Numerical dynamos that feed in mantle-style heat patterns recreate the same thing. Atlantic low spots, reverse flux under southern Africa, and surface lows where the mantle lid is hottest. Different tools, same longitudes. That's not coincidence. That's a chain. Edges do the damage. The blob's margins look steep, with ultra-low velocity zones that may be extra hot or iron-rich. In models, those edges act like rails. Core jets ride them, pile up flux, then peel off where gradients change. Put one reverse patch along the African edge and another under the mid-Atlantic, and you inherit two weak field rooms at the surface. That explains the split and the drift. As those reversed features slide beneath, the rooms wander in longitude. That dual-lobe split is the central mystery and the smoking gun. How stable is this deep blob? Big picture, long-lived. At the edges, lively. That's exactly where flow organizes and flux concentrates. So a persistent macro driver with active rims is the recipe for repeat magnetic weirdness over Africa and the South Atlantic. Surface rocks back it up. The Tristan da Cunha hotspot trail points to a deep source tied to the blob's crown. The South Atlantic Rift followed ancient sutures that now bracket the anomaly's footprint. African lavas and nearby islands record recurring low-intensity intervals in the same longitudes. North African archaeomagnetic curves show bursts of rapid change. The crust isn't steering the core, it's keeping score. Bottom line, the African blob doesn't cause the anomaly on its own. It sets the stage. The core is the engine. The mantle is the throttle and steering. In the last decade, weak field area grew, the minimum deepened, and one bruise split into two. At the same time, reverse flux converged under the hot longitudes. The alignment is too tight to ignore. Planning takeaway. The Atlantic Hemisphere is a preferred stage for magnetic weirdness, long-term lows, and lively variation. Not doom, a noisier baseline. Budget more margin. Treat drift as a feature, not a surprise. The hand on our satellites sits 3,000 kilometers down, hot at the edges. And it's not slowing down. Ancient receipts. Tree rings, ice cores, and magnetic rocks. Want proof the shield matters? The planet kept receipts. Trees shout. In 774 to 775 and 993 to 994 CE, tree rings worldwide spiked in carbon-14. Those Miyake events mean high-energy particles flooded the sky and made extra neutrons. The trees recorded it. Ice remembers. Greenland and Antarctic cores hold layers rich in beryllium, tin, and nitrates, cosmic ray fallout. Some layers match the tree spikes. Others trace stormier decades. It doesn't mean the field vanished. It means when the magnetosphere slackened or the sun surged, the chemistry of the air changed enough to leave marks. Clay tells stories. When ancient pots were fired, iron grains aligned with Earth's field of that moment and froze it in. Later, archaeomagnetism reads the direction and strength. Across the Levant, North Africa, and Europe, you see calm stretches broken by fast swings. In North Africa and the Middle East, some swings are sharp, regional quirks that rhyme with today's Atlantic sector oddity. Now the big stumble. About 41,000 years ago, the Lachamps excursion dragged the dipole down to maybe 5 to 10%. Polarity briefly flipped and snapped back in centuries to a millennium. Lavas captured wild directions. Sediments traced a global reshuffle. Ice cores show isotope spikes. The cosmic ray gate opened wider. Models suggest more nitrogen oxides, some ozone thinning, more UV at the surface. Not an apocalypse. People and ecosystems kept going. But a stress test you'd feel if you flew satellites or needed flawless navigation. Between spikes and stumbles sit lesser dips. Mono Lake, Gothenburg. Sediments show kinks. Paleointensity sags. Isotopes nudge up. The pattern, the dynamo stumbles often enough to matter. When it does, cosmic weather talks louder. The Atlantic won't drop the theme. Basalts from Tristan da Cunha and nearby islands erupted during weak field windows and carry low paleointensities. Seafloor stripes hide subtle asymmetries that, even after corrections, hint at intensity differences in the same longitudes that host today's dent. The crust isn't causing the anomaly. It's keeping the journal. What does it add up to? Comfort and warning. Comfort. Even in Lachamps, Earth kept air, water, and life. Warning. Our weak point is tech. Weak field corridors let in more radiation right where we stack satellites, navigation, and long wires. Scale check. Tree ring spikes are one-year punches. Ice core decades are storm seasons. Excursions are century-scale weak phases with messy geometry. Reversals smear over millennia. Today's dual-lobe over the South Atlantic is none of those extremes. It's a regional sag with a deep driver growing and splitting on decadal beats. Satellites can track it, operators can plan for it. The practical lesson, the past, sets expectations. A living dynamo throws odd years and odd centuries. When the field thins regionally, space weather talks louder. When it thins globally, the sky changes without ending the world. Read the ledger in wood, ice, and fired clay, and build margins that respect a shield made for lungs and lichens, not for silicon and copper. The big fear, pole reversal versus excursion versus doom. This is where headlines get loud, so let's sort the buckets. First is the life we're in now, secular variation. The core's flow rearranges magnetic flux over decades, the global dipole eases a few percent per century, and regional dents like the South Atlantic Anomaly deepen and drift. Compasses don't spin, they wander slowly. Satellites feel more radiation over specific longitudes. Operators respond with procedures and parts. It's noisy, it's manageable, and it's the backdrop for everything else. Next comes an excursion, the stumble with teeth. The dipole weakens hard, often to a sliver of its usual strength, and the geometry of the field tangles for centuries or less. Poles migrate far from their typical homes. Sometimes the polarity briefly flips, then snaps back. Lachamps around 41,000 years ago is the case study. Cosmogenic isotopes spiked, auroras wandered to low latitudes, ozone likely thinned some, and more ultraviolet reached the surface. It wasn't extinction, it was a stronger amplifier. If we'd flown satellites then, we'd have lost a lot of nights and redesigned quickly. Finally, a full reversal, the long dance. Polarity switches and stays flipped for hundreds of thousands of years, but the process is smeared over millennia. Strength sags and recovers in chapters unevenly by region. The fossil record doesn't pair reversals with mass extinctions. The atmosphere doesn't blow off. Life keeps going. For a civilization built on electronics, a multi-century weak phase means chronic friction. More satellite faults, more radio blackouts during storms, more grid precautions, more navigation days that step back to older skills. So where are we? Not in a countdown to a Hollywood flip. Modern models show reversed flux patches migrating beneath, southern Africa and the mid-Atlantic, and a dual-lobe anomaly at the surface that tracks that movement. The global dipole has eased since the 180s, but it sits far above excursion-class lows. The pattern reads as vigorous secular variation plus a regional sag, not a committed plunge. Could an excursion emerge from the same dynamics without much warning? Yes. Excursions in the record don't preface themselves with centuries of trailers. They materialize from reorganized flow, flux gathered, jets rerouted, and the signal at the surface crosses thresholds fast on human scales. The timelines matter. Design cycles and budgets live in 5 to 10-year windows. Grid upgrades land in similar beats. Excursions unfold in centuries to less. Reversals take millennia. That mismatch is the anxiety. We don't need prophecy. We need posture. Satellites sit at the top of the risk stack because they live inside the problem. A patchier, weaker field expands the real estate where high-energy particles intrude. Upsets climb, downtime grows, selective hardening and smarter autonomy buy back time. Navigation sits in the middle. Ionospheric weather gets rowdier when storms couple into a ragged field. Integrity flags do their job. When they slip, procedures take over. Grids feel the field through long conductors. Lower strength and faster gradients lower the threshold where geomagnetically induced currents become trouble. Series capacitors, grounding tweaks, and conservative operations hold the line, but the nuisance budget grows. The human health picture is more local and honest. Ozone governs ultraviolet at the surface. A dented magnetosphere doesn't sunburn a city. Aircrew dose planning gets sharper during solar particle events and in corridors where particles ride lower. Regulations track it and dispatch adjusts. The biosphere handled last shamps and lesser wobbles. Our fragile species is silicon. Geography is destiny for a while. The Atlantic sector has warned magnetic oddities more than once, and the eastern lobes drift toward Africa is today's proof. That shifts operational weirdness toward those longitudes first. More avoidance minutes in orbit, more GNSS hiccups on some days, more grid advisories on moderate storms that used to feel minor. Then the engine reorganizes and the stage moves. What about headline-grabbing ideas, inner core rotation changes forcing flips, sudden switches, end-of-world talk? Interesting research lives at the edge. Reality lives in evidence. The hand we can see is the mantle's heat pattern steering core flow. Decadal maps show the dents forming before hardware feels them. That's enough to plan against, so the fear shrinks when the plan fits the clock. Treat core weather like hurricane season. Forecast the dents with satellites and observatories. Harden where it pays. Write rules that assume memory will lie and timing will slip on the wrong nights. Accept inefficiency on the days that buy resilience. If an excursion ever announces itself, it will be in the math first, not the movies, and the playbook will already be open.